I'm going to start off the first theme session this morning by introducing this topic, synchrotron-based studies of high-pressure mineral behavior. And I thought I'd just start off by giving a brief intro slide. First of all, introducing our speakers. Chumik Dara from the University of Hawaii will be presenting the talk, Putting the Squeeze on Silicate Chains, Unusual Coordination States Accompanying the Densification of Pyroxenes and Amphiboles. And that'll be followed by a presentation by Zhang from the University of New Mexico. And her talk is titled Elastic Anisotropy and Phase Transitions in the Earth's Upper Mantle. Both of these talks and their participation in this meeting, and by the way, I really thank the organizers for putting together this great event. Yesterday was fabulous, such great talks. Yesterday evening was wonderful. In any case, the organization Compress is supporting this particular theme this morning. And just to remind you what Compress is all about. Compress is an acronym, actually, and it stands for the Consortium for Materials Properties Research in Earth Sciences. And this is a photo of our annual meeting. The last one was held outside of Albuquerque, and you can see the Sandia Mountains in the background. And this is a good representation of our community. The Compress is all about the community. It's a community-based consortium that's funded by the National Science Foundation to enable earth science researchers to conduct the next generation of high-pressure science on world-class equipment and facilities. And in particular, what we are focused primarily on is leveraging the facilities and the opportunities that are present at some of our synchrotron facilities that are run by the DOE. And Compress has beamline scientists and experimental stations on these three synchrotrons: the Advanced Light Source at Lawrence Berkeley National Lab, at the Advanced Photon Source at Argonne National Lab, and the National Synchrotron Source 2, the new synchrotron, at Brookhaven National Lab. And just to wrap it up here really quick, because this is about the talks, not about me giving a presentation, but I just wanted to let you know that the main types of experiments that we do, although this is not exclusive to Compress, but the things that we use primarily to achieve very high pressures on the synchrotron beamlines are the diamond anvil cell, the DAC, and the multi-anvil press. And here's just a list of the current projects right now that Compress is funding. We have 12 of them. The majority of them are beamlines, basically beamlines that have been in existence for quite a few years, producing what we think is extremely high-quality science. And as an example of that high-quality science, I'd like to hand it over now to the speakers, Chumik and Jin. Thanks a lot.
My name is Zhang. I am assistant professor from University of New Mexico. As a more junior PI, junior person, in this audience, I feel like I learned so much yesterday. I really appreciate everything like you guys prepared, and that saves me like one day yesterday. Sitting here listening to all the talks saves me like days, to read papers. Seriously. So today I feel like super happy that I can also share some of the stuff that I know more about with all of you guys, so that I can keep you guys happy as well, so I can learn more today, later today. So the talk title is a little bit different from what Carl talks about, because I feel like since Chumik talked so much about phase transitions, I'll probably stay a little bit away from phase transitions and then more focused on the physical properties of the like Earth materials. In this case, the stuff I'm focusing on is this mineral called amphasite, which is also a pyroxene. And I'm going to talk a little bit about the anisotropic elastic properties of amphasite and explain how would that help us to basically detect the ecologic materials in the Earth interior. It is a collaborative project between our group from New Mexico, which is over here. These are my students, lovely students, with a bunch of collaborators from other institutions and organizations. And this is Chimic's picture. I know it's a little bit old, but you've seen him just a few minutes ago. Okay, so all my collaborators over here. So just give you a little bit background about what I'm going to talk about today. So we know the Earth is just like onions, right? It has layered structures. But the Earth is also a lot more complicated than onions because we have a lot of dynamic convection, dynamic processes happening in the Earth interior. This big picture basically shows is a geodynamic simulation. Basically shows you two chemical petrological end members. Blue color indicates Harzburgite, so it's a more refractory end member, petrological end member of the Earth interior. And the basalt, which is eclogite, is a more fertile end member, red color over here. You can see all these two end members are mechanically mixed, like everywhere in the Earth interior. These two end members are the major chemical heterogeneities we have. So when we're looking at this kind of pictures, there are three physical properties I care most about. So the first one, of course, is the density, because the density contrast basically controls the movement of materials in the Earth. Denser stuff sinking down, lighter stuff moving up. The other thing is the seismic P wave and shear wave velocities, which helps us to identify those chemical heterogeneities. Basically because seismology is still by far the only tool we have that can image the three-dimensional views of the Earth interior. The last one is seismic anisotropy, which actually can reflect the flow directions in the Earth. As long as you have any kind of dynamic flow in the Earth interior, such as these flow lines showing here, you will have either a lattice preferred orientation, we call LPO, of crystals, or you will have shape preferred orientation, or maybe end, of shape preferred orientation of melt pockets or frozen melt, some kind of things like that. Either one of these can produce the seismically observed anisotropy. Today, we're going to talk the more relevant, or the ones I care most about, is lattice preferred orientation here. In order to explain the seismic anisotropy, requires two kinds of information. The first information, of course, that is the texture. Basically, how the mineral grains and crystals grow and orient, like under the sort of like a stress field like this. The other information we want to know is basically how the velocities change. Basically, a mineral grain like this, how the velocity is going to change as a function of directions within that individual mineral grain. Combining these two, we can know the seismic anisotropy. This information over here can be described by single crystal elasticity, which is the fourth order elasticity tensor. With this information, we can calculate the seismic velocities and anisotropy here. And if we want to know the density, we need to know the information of equation of state of these mineral phases. So in order to know the equation of state, listed over here, we utilize the synchrotron-based single crystal X-ray diffraction plus diamond cell technique to generate high pressure and the resistive heating to generate high temperature. These kind of experiments can, of course, we can solve the structures if we have enough diffraction data, like what Chimic showed, that you can solve investigate different kind of phase transitions. But the other information you get, direct information you get, is density. We can also get some insights about the anisotropy of a single crystal, from different compressibilities along different directions. Most of my experiments was performed at Jessica's sector 13 BMC. This is a very nice image about the hutch, of the sector hutch, and then this is the operation desk over here. And this is the facility funded by both Compress and Jessica's, and Chimic is actually a PI of this facility as well. So once we can get some insights about anisotropy, right, from this kind of experiments. Some other things, if we want to know the details of the anisotropy of individual mineral grains, we need something else. That is, we use the Bruin spectroscopy to measure the single crystal elasticity of individual mineral grains. This is a picture to showing basically my lab at UNM, and we can use, again, diamond cell to generate high pressures. Temperature can be generated by either resistive heating or CO2 laser heating. into the diamond cell. And this is a small video showing you laser heating the ice inside of a diamond cell. So the concept of Brilliant spectroscopy is not that difficult. Basically what it is we can shoot a single frequency laser into a diamond cell sample chamber over here, and then we collect the scattered light. The scattered light will have several different frequencies. The frequency shift between the inelastically scattered light and the elastically scattered light is proportional to the velocities propagating along this probed phonon direction over here. This is velocity, this is a frequency shift. Okay? And if you think about it, if you have a single crystal like this is your probed phonon direction. If you can rotate your crystal within this plane, then you can actually measure the sound velocity along all different kind of crystallographic directions, right? In this case, if you have a hardworking graduate student, or you are hardworking, we can collect a bunch of P-wave and shear wave velocity data along different crystallographic directions. And by inverting through this Christoffel equation, we can get the full fourth order elasticity tensor of this crystal. And then through some kind of averaging scheme, you get the Box shear modulus P-wave shear wave velocities, and take one step more, you can calculate the anisotropy, what people is gonna see, seismically. So, getting back to the results about amphasite. Okay, why do we care about amphasite so much? If you think about a simple kind of a view of the Earth, that we tend to believe that the Earth's ambient mantle is made of this olivine-rich rock called perlite. Okay, but when you have subduction going on, the subduction oceanic crust is made of basalt. When you compress it, subduct it into the Earth interior, the basalt is going to convert into a rock called eclogite. And eclogite, as we talked in the introduction part, is one of the major chemical heterogeneities in the Earth interior. If we want to locate this eclogite at different locations from seismic studies, we need to know how different in terms of seismic properties, between eclogite and the perlite, basically between the slab crust and the ambient mantle, how different they are in terms of seismic properties. That's a very important thing we want to know. If you look at the constituting minerals of eclogite, there are three major mineral phases: garnet over here, amphasite over here, and also silica polymorphs, which are sort of like more minor phases. And this kind of a mineral assembly is stable up to about 500 kilometer depths before it transformed into garnetite. So among all these three mineral phases, amphasite is actually the most abundant one. It's up to about 70% volume percent of eclogite. It could be more. But amphasite is the least studied mineral among all these three minerals, least studied ones. Why is that? Partially because it has very low symmetry. It's monoclinic over here, like what I'm writing over here. So how poorly studied it is? Even right now, 2019, right now, we still have no high pressure single crystal elasticity data, for amphasite. No. And also, we know amphasite is a solid solution between diopside and jadeite, which we know the substitution of sodium, aluminum with the magnesium, calcium can stiffen the crystal structure, but whether this kind of solid solution is close to ideal mixing, which means it's a linear trend or not, we don't know. We know the end members quite well, but we don't know too much about something in between. Lastly, if we put some hydrogen into the crystal structure, how is that going to affect the seismic properties of amphasite? And further, of course, the eclogite. We don't know either. So I'm going to focus on these three questions over here. So we performed a series of experiments. The first one is related to this amphasite crystal containing roughly 30% of jadeite component. And here's the aggregate thermoelastic properties of amphasite. This is from the sound velocity data, so adiabatic Bock shear modulus compared with diopside. And this is isothermal thermal equation. This is the thermal equation of state data we collected from the synchrotron. These two sets of experiments formed a very coherent, inclusive thermoelastic data set for amphasite containing about 30% jadeite component. Comparing with the diopside end member, it looks like the shear modulus is almost identical within the entire pressure range, whereas the bulk modulus is slightly higher, which is as expected because you have a stronger jadeite component in it. If you take a detailed look at the diffraction data, this for simplicity, I just pull out the 300K data over here. Look at the compressibility along 3 different axes. You may notice that the A-axis is the least compressible, whereas the B-axis is the most compressible axis. This kind of observation suggests that the omphacite is actually very strongly anisotropic. That result is consistent with the single crystal elasticity measurement we performed using boron spectroscopy. C11 compressibility, incompressibility along A-axis versus B-axis is clearly higher, and this difference is getting higher and higher as you're going to, higher and higher pressures. Since it is a monoclinic crystal, we have 13 independent elastic moduli for omphacite. Most of these elastic moduli increase with pressure. There's 2 really weird ones, C35 and C46, actually decrease with pressure. This is quite interesting because that tells you that as you're compressing the material more and more, it actually becomes, along certain shear directions, it becomes easier and easier to deform. So with all these data, we have so far for omphacite, finally we were able to model the elastic properties or seismic properties of eclogite, surprisingly, for the first time based on laboratory data. So these are the results showing over here. So the black dashed line showing the parallite, basically ambient mantle data along a regular mantle geotherm about 1600 K adiabat. The blue and red dashed lines are for eclogite. Blue lines indicate subduction kind of a geotherm, colder geotherm, and red lines indicates regular mantle geotherm. First one, of course, the density. If you can see over here, no matter whether it's along hotter or colder geotherm, the density of eclogite is definitely a lot higher, about more than 10% high, roughly 10% higher than the ambient mantle. So which again confirms that the eclogite is a main driving force for the subduction. The other things you can look at is the P wave and shear wave velocities, as well as P wave anisotropy and shear wave anisotropy over here. The contrast between the eclogite, which is this blue line, versus parallite, which is black line over here. Isotropic velocities, anisotropy, the largest contrast always happen between 310 kilometers and 410 kilometers. So what that tells us is, with this big contrast over here, this is actually an optimal depth range for seismologists to search for the eclogite in the Earth's interior because we have such a big contrast over here. And another thing I want to point out from this result is, when we're talking to a seismologist, they show us these beautiful pictures with blue and red colors, right, of the Earth interior. And if you talk with them, they see blue colors, you will say, yeah, it's faster, velocity faster, then it's colder, temperature is colder. Red color is slower, then temperature is higher. And then that's usually their explanation. So you can do a simple kind of conversion, how much faster it is, and convert to how much lower the temperature it is compared with surrounding mantle. But this kind of simple conversion is based on just temperatures. When you are putting compositional effect into account, for example, in this case, especially between this 300 to 400 kilometer depth range, that the eclogite velocities are so much higher than parallite. So that if you don't consider compositional anomalies, your estimation could be off by several hundred K. That is not a small number. On the other hand, if you're looking at within the transition zone, which is 400 to 500 kilometer depths, the velocities of eclogite and the surrounding mantle are very close. So which means any kind of blue anomalies within this transition zone, if you believe even it is eclogite over there, you can do a simple conversion just based on temperature because compositional effect is not as much if you're going lower than, deeper than 400 kilometer depths. Some other information. So in addition to slab crust, we might also have eclogite from some other sources. For example, like continental root delamination, that kind of process, right? It's more toward the mafic side for the lower crust. So if some conditions happen, give it to a little bit higher pressure or some kind of process happened, these rocks may transform into eclogite. And then the eclogite over there carrying some continental signatures will have a slightly different composition. For example, the higher aluminum content will lead to higher jadeite component within the amphasite mineral grain. So how does that affect the velocities? This is a study to show that basically how the velocities or elastic properties change within the diopside jadeite solid solution. This end is jadeite, this end is diopside. How different it is? These two end members can differ by almost actually over 30% for elastic properties, over 30% difference. That is huge. This is a comprehensive analysis, including a bunch of single crystal data, our data or previous people's data together. The red shaded area shows you the 95% confidence interval. Most elastic moduli are following this sort of a linear trend, except C13 and C23, these two. All the others follow this linear ideal mixing trend. With this, we can calculate how different seismic velocities is for a more oceanic-like eclogite versus a more continental-like eclogite. How big the difference is the velocities? You can see over here. The change in shear wave and P wave velocities are 150 to 250 meters per second. That's approximately almost close to 3%. That may not look like a big number, but it is big for seismologists. So with it, if this 3% difference persists as you're going deeper at the increasing pressure and temperature, it can be actually a good tool for us to trace the petrological origin of eclogite. If you know there is an eclogite over there, then you can backtrack where it is, because the difference between these two different kind of eclogites. So one other last information I want to provide is when you're looking at this kind of subduction environment, we know subduction zone is a major water carrier for you to bring water down into the earth interior. And we know the structural water can lower minerals' elastic moduli or the P wave, shear wave velocities. That's quite significant for wazite and ringwoodite, as we know from yesterday's very nice talks about diamond inclusions. Those contain a lot of water, and people believe that, people have measured it. It looks like it can decrease the velocities of those materials, including olivine as well, has been confirmed. And among all the upper mantle anomaly anhydrous minerals, clinopyroxene actually has the highest water solubility. So it makes sense for us to ask, if we put water into clinopyroxene, in this case amphasite, how much is it going to affect the seismic properties? So we did a set of experiments on a amphasite sample with about 40% jadeite component, but 700 ppm water. That is not super high, but it's sort of moderately hydrated, reasonable number hydration in amphasite. The result is shown in these yellow squares over here. You can see that although some off-diagonal or shear-related elastic moduli, such as C13, C25, C66, something like that, shows a little bit lower, values than definitely off the 95% confidence interval, right? But if you're looking at the bulk modulus and shear modulus, the average, the aggregate properties, these are spot on the trend, which is quite different. That means hydration almost have no effect, at least up to 700 ppm water has almost have no effect, which is counterintuitive a little bit to me. That is very different from all the other anomalous anhydrous minerals such as olivine, wazite, and ringwoodite. So with all that, this is a summary file over here. And I need to thank the funding agencies, of course, the National Science Foundation, and also my startup from UNM for supporting my research. And thank you very much for listening to me. Okay, I'm happy to answer.